Okay, so one thing with the formulas, and I mentioned this in the isomer video, is when you have a CnH2n plus 2 formula, that's an alkane formula, right? As kind of, as maybe a comparison, like CnH2n would be like an alkene, or it could be a cycloalkane. This has to do with, unsaturation. There's one little caveat with that, which is when you have halogens, like fluorine, chlorine, bromine, they actually take the place of a hydrogen. So that F there means that this formula is really like C4H8. It's basically halogen kind of replaces hydrogen. Does that make sense? Let me know if that's unclear. One thing to maybe compare that with would be oxygen, where oxygen would not. So you could have something like C4H8O, and you basically kind of disregard that O. This would follow the same formula pattern as that. So that would be like an alkene or a cycloalkane. Halogens, though, it doesn't work the same with the structure and how they kind of work. So what I'm thinking with this is that a structure of an alkane, or no, that's not going to be CnH2n plus 2. That's going to be like this one, right? Let me know if that's unclear. So I'm thinking with that kind of C4H8 type formula that I'm going to have alkenes or rings. So with structural isomers, then we're getting into kind of the pattern of like 4 carbons you could have in a row, or you could have 3 carbons with a branch, right? And that would be like a methyl propane type thing. And then what we have are possibilities of where we put the fluorine. So let's maybe do this with these straight butane chains first.
Quick question.
Yeah.
For the one you drew as like a triangle with the 3, why is that a methyl propane, not you said, like you said, and not a an isobutane?
Well, now you're getting into what's called a common name. So this can commonly be called isobutane. And that's where with organic chemistry, you get into this whole kind of like can of worms with what some people use. It's like water, right? We would say water, but systematically you'd say like dihydrogen monoxide, right? Just a different way of naming it. We're going to stick with systematic names because that's what you're tested on. So this would be systematically named like 2-methyl propane, because the longest chain is 3, right?
Okay, yeah, that would make sense. So are we going to be using like the that like PERT, P-E-R-T terminology as well?
That will be used for substituents. Yeah, so you could, on like if you have a long chain, let's say like 6 carbons, like a hexane, you could have a branch off of that was a propyl, let's say, or an isopropyl branch, which is just like a different form of 3 carbons branched off. So yeah, we do use like isopropyl, isobutyl as substituent names. Those are still considered like systematic. Does that help?
Okay, yeah, thanks for clearing that up.
Yeah, so kind of like to make this the most maybe efficient way of kind of going through this, like the fluorine that's in this, you could put off of the first carbon, right? It would be like one fluorobutane, or I could put it off the second carbon. Sorry, I was saying this is an alkene, so I need a double bond. So let's say the bond is right here, right? So this could be one fluoro, 1 butene. This would be 2 fluoro, 1 butene, right? Then I could move the fluorine here, and then this would be 3 fluoro, 1 butene. And I also have a possibility of putting the fluorine at the end, which would be 4-fluoro-1-butene. Right?
I have a question.
Yeah.
So is isopropyl and propyl, are they considered isomers of structural isomers of each other?
Yes. Yeah. So
Okay.
structural isomers is like you're moving the carbon connections around. So you're changing like the numbers of where the fluorine is or where a methyl is. That's what we want to think about. You're changing kind of the structure of where a branch comes, like which carbon's coming from. Right. So with the alkenes, these problems get pretty gnarly because I can now put the double bond off of the second carbon. So this would now be 2-butene, right? That makes sense? And because I still have a fluorine, then I basically get into, again, where I can put the fluorine. So like this problem, you actually have kind of these two variables where variabilities where you can move the double bond different positions and the fluorine, right? If I do this, is that different? So this would be like 2-fluoro-2-butene.
No, it's the same.
It's the same because I would just number it from this side, right?
Yeah.
So there's no such thing as 3-fluoro-2-butene. And if I did that, that's actually the same as this one because I would just number it from here, right? Make sense?
So your top one is wrong then.
Say it again.
So the top one that you did here at the top, where you had 3-fluoro-1-butene.
No, that's different because the double bond is still off of
okay.
one. Yeah.
I see.
Yeah. Now we have one or a couple where we can put the double bond here with a branch, and then you can put the fluorine here. And then I'll just I won't really name these because you can, I think they're in the solutions manual. You can look at them there and kind of practice on your own. But those would be two different structural isomers where you have a methyl propene and you can put the fluorine different places, right? So there is the added layer of now you can do rings. So you could do a 4-membered ring with a fluorine. Wouldn't really matter where you put it because it's still going to be the same or anywhere. And then you could have a 3-membered ring with a branch, a methyl. And then I'm just realizing now how much this problem sucks. Because you actually get 3 of those possibilities. Wow. Again, all have different names. If you number them and name them, you'll see that they're different. So what? That's 12 structural isomers. I think that would be like way overkill for a test problem. You know, I think like it's just too time consuming and too hard basically. But it's kind of good practice to just go through and see like if you can see the differences between these, and then again naming them helps to do that. Any questions on the structural isomer part? No, everyone's just kind of now intimidated.
Putting the fluorine in a different place.
Yeah, and the double bond and like the structure of the carbon chain, because again, if you have that C4H8 formula, that's the CnH2n, right? That is like unsaturated, we'd say, because it's not an alkane. So you could have an alkene with double bond or a ring cycloalkane, a ring with all single bonds.
Okay, yeah, I get it.
Yeah, that just kind of helps you because you don't have to go through and like count all the hydrogens. Like these are all going to have 7 hydrogens. You go through and put them in, right? Just basically allows you to just do the carbon backbone, right? Just worry about that. Now the geometric isomer part, go down here. So that would be like the second part, geometric isomers. With organic chemistry, does anyone remember when you would have geometric isomers?
Double bonds.
Double bonds, yeah. So you actually can have them for rings. Not all the rings. We're not going to really cover that because that's skipped over pretty much in Chem 1C. If you get to OChem, you can do that. But with the double bonds, what you want to do is go through. This also can be kind of tricky, so I'll kind of try to do it in an efficient way. You want the double bond to have two different things on it. So you need that double bond there to be basically like these two things are different, and then this thing has different things. I'm just going to use letters here. So like 1 doesn't equal 2 and X doesn't equal Y. That's when you have cis and trans. So if let's just pick this one here. Does that have cis and trans isomers?
Which one?
This one here.
No,
Why?
because there's just carbons attached to it and one hydrogen.
Well, so on this carbon of the double bond, there's 2 hydrogens, right? They're not shown, but those are 2 hydrogens, right? Those are the same thing. So if I switch those around, you can think about that doesn't change it, right? If I change those, it's the same thing. That, that's why this rule, these 2 things have to be different, and these 2 things have to be different. So that one would be, no cis trans, no geometric isomers for that one. Same thing actually for this one here, because these are 2 methyl groups, which are the same, right? So if we go and look at like the top row of the first ones we did, I'll just circle the ones that have geometric isomers. So that one does, because carbons 1 and 2 have different things on them. What about the next one?
It doesn't have one.
Doesn't have it, right? Because this has 2 H's. The third one here doesn't, because this one also, carbon 1 has 2 H's. Fourth one, also this one has 2 H's, so that one doesn't have it either. In the second row, what about the first one here? So we're looking at this one here.
Anybody familiar with these chlorine biscuits?
Would it be?
It does have it.
It does have it, yeah. Because again, carbons 2 and 3 of the double bond, they each have different things. If you want to draw them in, you have an H and that, you have H and that, different things. And also this one as well, those 2 carbons of the double bond have different things. And I'll let you try and draw the cis trans. You can just flip one of those around, look in the solutions manual to see also if you want to check your work. But you would just, again, to draw like cis or trans isomer, you would just basically flip. You can flip either a carbon of the double bond, just change those groups around. So 3 of these would have geometric isomers, 3 of the 12 structural. Here we have the review questions. So number 6 is a colligative properties problem, and it's like change in freezing point kind of question. So we have our formula. I always use the negative. I know this is kind of confusing because the book doesn't use it, but that just kind of tells me this is lowering the freezing point, right? The change is a negative change in freezing point.
Yeah, I was just wondering because like the answer is B, but C is K3PO4, which makes it seem like it breaks into like 4 ions, but that's not the answer.
Right. That's kind of why I chose this question, because typically, well, the thing that's going to be important with colligative properties is it's the I times the concentration, right? That's the driving force for like whether it's the change in freezing or boiling point or vapor pressure or whatever, osmotic pressure, that I times the concentration. So what I normally would advise doing is just get in the habit of doing I, times like the concentration, whether it's molarity or molality or whatever. And then sometimes in the problem, it'll say like you have like 1 molar of each of them, right? And then it's like this is all the same, and then it's just the I value, right? Does that make sense?
Yeah.
So, but if it's not the same amount of moles, the moles of each is going to be one of the factors in that. So what you need to do is, it really wouldn't matter what weight you're starting with. You could start with 100 grams of each of them and do the same kind of problem. But that's different than starting with the same number of moles of each of them because they have different molar masses. So theoretically, we're starting with 0.45 or 454 grams of each of them, right?
Oh, okay. Yeah.
So actually, yeah. So if you turn using the molar mass, you want to basically turn those into moles of each of them, and then you can do like for A, I would be 2, and for B, I would be 3, and for C, I is 4, right?
Yeah.
But then you want to do that times and actually I've just uploaded an answer key or a solutions key for this.
Okay.
I wanted to get done this morning, but it's been a crazy day. But it's up there now on Gaucho Space, so you can look at my work. But you can use molality here. I just use the moles because it's proportional. And the point is that you need to do the I times like the moles you have, and then look at those numbers.
Okay, that makes sense.
Yeah, and that's like the quick kind of like reflex response is go with the biggest I value. But again, there may be fewer moles of that. So then, and if you work it out with the moles and the I value, that's why it's B. Problems. Yeah, so the isomer tree, which this will apply to chapter 19 or 21, is you have structural, where again it's like different things are bonded in terms of like attachments, right? And then stereo is just like different spatial arrangement of those things. So, a structural isomer. I think I've seen this in like a book somewhere, like an OChem book. If you took off your arm and your leg and you swapped them around, right? Then you've created a structural isomer. Does that make sense?
Yes.
Like where things are attached on your body, that's like a structural thing. Again, that goes back to like 2-methylhexane versus 3-methylhexane. You're actually changing the number of where that methyl is, right? Now, stereo, this gets broken up into geometric and optical, right? Because those are both different ways of doing things in space, and they have their kind of their own class, like the cis and trans way, which is just kind of an adjacent opposite. The optical is the mirror image. That's a more subtle difference. So that's just mirror images that are different, right? And then for chapter 21, we just stop here at structural. There's no further distinction. But for chapter 19, if you remember, we did kind of break this up. Does anyone remember those other 2 classifications of that?
Wasn't it like linkage and coordination?
Exactly, yeah. Coordination, which don't apply to organic chemistry. They're just not really used at all. But for chapter 19, with the coordination compounds, then yeah, we do use those, and they're specific to like coordination compounds and how ligands are attached to the metal, but they fall under this class of structure because you have different bonds that you might have like a metal attached to nitrogen and NO2 or attached to oxygen. So that's like metal attached to nitrogen is different bond than metal attached to oxygen, right?
Right.
Same with coordination. You're going to have like different ligands. You'd have a metal with, A ligands and B counter ions, and then you could have B ligands and A counter ions. You obviously have different things attached to the metal, different bonds, different structural different structures, right?
So you were saying that structural was the one that if you like switched an arm and a leg on a body, or was that the stereoisomer?
That's structural, yeah. So sorry, my analogy got cut off. So stereo would be like my arms are attached, but now like one's up and one's down, or one's up and one's down like that, right? So that's like if my arms were like this here and down there, and then that was like as locked, and then versus the other way, one up, left arm up, right arm down, and like that's the thing with the cis and trans, for example. Optical would be if I didn't change where my arms and legs were, but my mirror image was different, like it wasn't imposable, which tends to be because we're not completely symmetric. So, I have a tattoo on my left arm, so the mirror image is going to have it on its right arm. So if I took the mirror image out, it wouldn't match me, right?
Right.
That's an optical isomer.
Sorry, I had a question. I just was looking at quiz number 2 for Joseph, and it's about.
We'll do this one here. So it's an interesting problem because it's like a probability about a reaction and like what position you can kind of react at. You have one chlorine or chloroligand, if you want to use the correct term, on the cobalt compound with 5 amine ligands, and you're basically adding another chloride, right? So what it's doing, as you can see here, is it's replacing one of the amine ligands. This is essentially would be what we call like a substitution reaction. We kind of talked about that earlier with organic chemistry. And so this original chlorine is remaining the same. That's not being removed or changed. We're just adding, let's make this one purple, this chloride, adding kind of one chloride ligand, chloro. And so it could potentially replace any of the ammonias. So it could end up going any of these positions. And if I just kind of label them, like I think what I did on the answer key was, or solutions key was this. So like the position, it could end up in A, B, C, D, E, would give a certain isomer type, right? Because now I'm going to have 2 chlorines and 4 ammonia. So that product will have like cis-trans isomerism. So if that chlorine goes to A, the new one, would that be cis or trans?
Cis.
Cis, right.
Is
What
it
about-
possible for it to replace the other chlorine that's already on there?
It's possible, but in the reaction that's given, we're going based on this. It doesn't, right? Because
yeah, I see.
Yeah. So, but yeah, like in reality, that would be happening, and that would kind of just basically be like an equilibrium thing. They'd be like popping off and on. So what would end up being different is like if it replaced ammonia, and that's again based on the reaction. So if it goes to B, what would that be?
That would also be cis.
C?
That would that be trans?
So this angle between this C and this one is still 90.
Oh,
Right.
okay.
Because again, it's just we're looking at it.
But trans is only when it's 180, right? So it would only be at position E.
Exactly, yeah. So the isomer type you would expect would be A through D would give you cis, and only position E would give you a trans isomer, right?
Yeah.
So random probability says, which was what's going to happen when this thing is bouncing around and replacing ammonia, is that if we got whatever number of, if we got 5 products, we get 4 that would be cis and 1 that would be trans, right?
Yeah, I see that. And so the NH3 in the end, that is just like kind of like formality for the equation. It's kind of just there because we booted it out. It's not
Here,
on the
yeah,
outside.
exactly, yeah. This NH3 is just, yep, it's just like the one that got replaced. Yep.
Okay.
So that came from whatever position, yeah. So that's how we get the 4 cis to every 1 trans.